last class we looked at Gauss's law, which helps us in finding the electric field for a given charge distribution. If the charge distribution has some sort of a symmetry, then Gauss law can be used, or it can be exploited, the symmetry can be exploited to find the electric field. We saw a couple of examples of using Gauss law. One was the familiar infinite length line charge with a linear charge density of rho L coulomb per meter, and we found that the D field can be obtained by putting up a Gaussian surface which is cylindrical in nature, okay, and then the field was essentially going as 1 by r. So, it was inversely varying as r. Okay. We also saw another example of using Gauss law. This example was a infinite sheet of charges, okay, and then we took Gaussian surface as a small pill box. Okay. This is sometimes called as Gaussian pill box, and then we found that the field, because of this uniform surface charge distribution of charge distribution density rho s coulomb per meter square, was essentially independent of where you are located. So, it was independent of all the locations. Of course, these two are not realistic in the sense that they are not, you are not going to find infinite line charge or an infinite amount of plane charge, but they are good approximations for a long line charge or uniformly spread out plane of charges. Okay. We will continue with couple of examples of Gauss's law, and then we will look at what is called as point form of Gauss law. So, to recap, if you have already forgotten what Gauss law is, Gauss law states that the integral, the closed surface integral of a quantity d, okay. So, d dot ds, which is integral of this quantity d, which is called as the electric flux density and is measured in coulombs per meter square. So, this quantity, if you integrate over a closed surface, this should be equal to the total charge that is enclosed. Of course, the charge that is enclosed, if the charge is uniformly distributed in a region of space, will be given by the integral of the charge density over an appropriate integration. Why do I say appropriate integration? Because if the charge is spread out in a region of space in terms of its volume charge density, then you have to integrate the volume, okay. And if the charge is spread out over a line, then you have to integrate over the line. If the charge is spread out as a point, then as a point charge, then there is no integration involved, directly you are going to get the charge. I did not specifically mention the relationship between the surface that you have to use in applying Gauss law and the volume. For example, if I consider the point charge q, okay, so we know that the field lines from earlier Coulomb's law itself, we know that the field lines are going to go as 1 by r square. We also saw how to use Gauss law in this example, or we have not seen, it is fairly simple. You can assume a Gaussian surface, okay, that would enclose the charge. There are some subtleties involved in this one, we will come back to this subtlety sometime later. So, you assume a Gaussian surface of a certain radius, okay, as measured from the origin, and then you apply Gauss's law over here. Okay. Now, that will be the left hand side. So, you can assume a Gaussian surface which is spherical, because this is a nice spherical symmetry, you can apply, and then you get the left hand side, which would essentially be some dr into 4 pi r square. If your sphere has a radius of r, then the left hand side will give you dr into 4 pi r square, 4 pi r square being the surface area of the sphere of a constant radius r. Okay. Now, what about the volume? Should we actually talk about the volume of the surface that is enclosed? That is, if can I take the volume outside of the charge or outside of the Gaussian surface? So, if this S stands for the Gaussian surface that I have used in the calculation of the left hand side, then can I take the volume over here? No, I have to take the surface and the volume both to be the same, essentially saying that the surface S must enclose the corresponding volume that we are looking for. In other words, choose the surface and also see that the surface which is closed, you have to evaluate the volume of the enclosed surface. Okay. You can't choose a surface here and a volume somewhere else, these two have to be the same. Okay. So, this is some precaution that you have to take while you are solving Gauss's law. So, with this in mind, let us go ahead for one example of Gauss's law, something that would come up fairly later as an important example. So, here what we are looking for is a spherical shell of charge. Okay. This is a typical example that you are going to use Gauss law, which when there is a spherical symmetry. So, for these kind of problems Gauss law is very easy to apply. If you were to try and apply this one with Coulomb's law, you would struggle a little bit. Okay. So, if I consider a spherical shell and let us also assume that the shell is hollow. Okay. So, it is essentially the shell is made up of a conducting material and it is in the form of a nice sphere of radius a. Okay. So, on this shell, if you were to induce some charge by any of the charge induction process, you will see that this charge nicely distributes on the surface of the shell. So, the charge nicely gets distributed on the surface of the charge and then you want to find out the field everywhere. Okay. So, that is the problem that we are going to solve using Gauss's law. So, I have this spherical shell here. Okay. The shell has a certain radius, call that radius as a, and the charges are all distributed over the surface of this shell. Okay. So, the charge is all uniformly distributed over the surface of the shell. So, with a uniform charge density of rho s coulomb per meter square. Okay. Please remember that this surface area we are considering is actually spherical in nature. Okay. So, if you take the overall surface, which would be, the surface area of this sphere will be 4 pi a square, and if q is the total amount of charge, then the surface charge density is q by 4 pi a square. So, this amount of total charge is spread uniformly over the shell of the shell. Okay. Now, to apply Gauss's law, let us look at the left hand side. Okay. We need to of course choose a surface over which the D field will be perpendicular to the surface. It is not always possible, but if it is possible, you always choose a situation in which D field is perpendicular to the surface. What is the advantage of choosing D field which is perpendicular to the surface? Now, let us say for argument reason this is not correct. So, let us say the D field is in this way, okay, to the surface that you have chosen, or rather let us go back and write the field here. The fields will all be directed radially away. Okay. The field is directed radially away, but instead of choosing such a surface, a spherical surface, what I am going to do is I will choose a rectangular surface. Okay. So, I will choose a rectangular surface. Now, what happens? This part of the D field, which is of course originating from the shell, is not perpendicular to the surface area, right. So, there is some component of D that would be there along the normal to the surface, right. Similarly, over here the D field is not perpendicular. Here the D field is perpendicular, but such a line is only one, and probably on the bottom side there will be one. So, evaluating Gauss's law over such a surface becomes mathematically tedious, and that actually defeats the whole point of using Gauss's law. The whole point of using Gauss's law is to minimize the integration, the effort that you are going to put in the integration, and you can do that provided you choose a surface in which D is perpendicular to the surface, right. So, that dot product which is sitting between D and ds can be eliminated and it simply becomes a scalar integral. Okay. It is actually a scalar integral, but then the evaluation of the dot product becomes very easy to perform. So, this kind of a arbitrary surface, although Gauss law actually holds, is not well suited for our purpose because we do not want to increase our effort in integration. So, with that in mind, I am going to choose a Gaussian surface which is going to be spherical. So, let me redraw that Gaussian surface over here and apply the left hand side of the Gauss law, radius a. Now, I have to choose the Gaussian surface which also will be in the form of a sphere. Let us say I choose two surfaces. One surface I am going to choose inside of the shell. Okay. So, the center of this sphere will be the origin, and I am going to choose a surface S1, let us call this a surface S1, which is inside the shell. Okay. Now, what happens to the left hand side of Gauss law? Left hand side of Gauss law tells you that over the closed surface, if there was any D field over here, this must be equal to the total charge enclosed by the surface. Now, clearly the right hand side will be equal to 0 for this case. Why? Because this surface S1, you have to assume that this surface S1 is closed, of course it is closed, and then you have to see that there is actually no charge enclosed by this. Okay. So, there is no charge enclosed by the surface S1, and therefore, this will be equal to 0 on the surface S1 that we have considered. Of course, the surface S1 we did not specify what the radius of is. The radius of the sphere S1 could be anywhere from 0 all the way up to a, right. So, as long as r is less than a, which defines the surface S1, the corresponding integral over here will be equal to 0, right. Now, the integral is 0, does it actually mean that d is 0? That is an interesting question, right. So, if you are looking at this integral, the integral is 0, but what happens to the field d? Let us do this. On the surface, assume that there is a d field. If there is d field, then it would be perpendicular, right, to the surface, it would be perpendicular. So, if this is a sphere, all the lines which are along the radial direction will be perpendicular to this surface of the sphere. So, what is the incremental surface area that we have on the surface of sphere S1? That incremental area will be directed along the radial direction, and that is given by r hat. Let us call the radius of this one as r itself. So, I have r square sin theta d theta d phi. Okay. Please do not get confused between this r and this r. This r actually stands for the radius of the sphere S1. Okay. And d has only the r component or the radial component. So, that becomes r hat dr. So, if I consider the dot product between the two, I am going to get dr and then r square sin theta d theta d phi integrated over the sphere radius, right. Now, I also know that my d field does not depend on theta and phi, because of the symmetry conditions. The d field does not depend on theta and phi. Okay. So, dr will essentially be constant over the surface and actually can be moved out of the integral, and the remaining portion of the integral will simply give me the surface area 4 pi r square. So, I actually have a constant dr, that is dr is constant over the surface, that is getting multiplied by the surface area of the sphere S1, which is 4 pi r square, but the right hand side of this is equal to 0 because r is less than a, right. Since this will not be equal to 0, right, the only conclusion that we are going to have from this expression is that dr must be equal to 0 inside a. So, inside a hollow shell, dr will be equal to 0, the radial component of d, which is the only component of d, that will be equal to 0. But we also know that if the material is made up of some homogeneous material, or if it is just free space or air, then the material will be described by the constant epsilon 0, the permittivity of the medium, which relates dr and er, right, the radial component of the electric field. So, if dr is equal to 0 and epsilon 0 is not 0, which simply implies that er will also be equal to 0. So, as long as you are inside the shell, the electric field components will be 0. Okay. All right. So, this was for the electric field component inside the shell. Now, what happens if I choose the Gaussian surface outside of the shell, right. So, outside of the shell, if I choose, what will happen? So, let us say I choose the Gaussian surface, let us call that as S2. Okay. This has a radius of r again, in this case r is greater than a. So, if I choose this surface, call this as S2 as the Gaussian surface, which is outside of the shell, and there are of course charges on the shell, let us write that one, otherwise this becomes like 2 circles written and we will lose what we are actually trying to solve. Okay. So, this is our situation. We have chosen a surface S2 which is outside of the shell. Okay. So, what would happen to the right side and the left side of the Gauss's law? The left side again will have a situation where the d fields will be radially directed, as well as they would be constant on the surface S2. Okay. So, they would be constant on the surface S2, allowing us to rewrite this d dot ds integral over the closed surface now with respect to surface S2 as dr 4 pi r square, 4 pi r square being the surface area of S2. Okay. Please remember that r is greater than a. So, this is the left hand side of Gauss's law. So, what happens to the right hand side of Gauss's law now? You must now see that this should be equal to the total charge enclosed by the surface S2. Now, there is no charge in the intermediate region over here, right. The amount of charge that is enclosed must come by integrating the charge density over the surface area of the sphere, which is the original shell of charge that we were considering, and that original shell of charge has a radius of a. Therefore, the right hand side becomes rho s into 4 pi a square. Is that correct? So, the right hand side will be equal to rho s 4 pi a square. Okay. So, that is the total charge that we have. Okay. So, now we will simply equate the left hand and the right hand side of Gauss's law, thereby getting dr as rho s 4 pi a square divided by 4 pi r square. So, 4 pi in the numerator and 4 pi in the denominator go away, and you are now left with rho s a square by r square. Okay. So, this is the radial D field. The electric field E r, again assuming that the medium outside here is filled with epsilon 0. So, the radial electric field E r will be equal to rho s by epsilon 0 a square by r square, provided r is greater than a. Now, at r is equal to a, if you see from the surface S2, see what happens as you come close to a, from shrinking S2, which was originally with a radius r, to sphere of radius a. So, what happens as you start shrinking S2, that is, if you come outside of the sphere, if you start coming towards the shell, spherical shell of the charge that contains. So, what would be the value of the electric field predicted? The value of the electric field predicted will be obtained by writing r is equal to a. So, when you substitute r is equal to a, this fellow will become rho s by epsilon 0, right. So, from the outside of the shell, as you start moving towards inside, you are going to predict electric field of rho s by epsilon 0. However, if you remember what we have done couple of minutes earlier, inside the electric field was actually equal to 0, right. So, if you now start expanding the surface S1, so you start expanding the surface S1, which means that your r, which was the radius of the surface S1, now becomes closer to a, that electric field will become, that electric field will still be equal to 0. So, there is some amount of discontinuity between what the values you get when r is less than a and you approach a from the left hand side, and what you get from r greater than a and you approach the shell on the right hand side. Okay. So, this discontinuity in fact gets this discontinuity is not completely incorrect, because that is precisely the amount of discontinuity that is required to maintain the charge distribution. Okay. We are going to see this type of discontinuities when we discuss boundary conditions later, but for now remember that this discontinuity is the reason why there is a charge distributed on the shell. Okay. So, if you want to sketch, you can sketch the electric field. So, let us sketch the electric field as a function of the radial distance r. So, you will see that until r is less than a, there will not be any field. At r is equal to a, the field will be equal to rho s by epsilon 0, okay, and then it starts to go away as 1 by r square. Okay. So, if you are very far away from the spherical shell, the charge would essentially be 1 by r square, and the entire charge would look as though it is coming from center of the spherical shell. So, it looks like the entire charge that was actually distributed on the surface is actually concentrated on the point at the center of the shell. Okay. Now, what about the potential V of r? We know that the potential and electric field are related with each other, and you can actually calculate what is the potential. The potential for an electric field which is going as 1 by r square will go as 1 by r, right. So, this is similar to the point charge potential that we have seen. So, you can calculate that potential which you can obtain by integrating the electric field from one point to another point, and taking the point of the origin as infinity and considering all the potentials with respect to infinity as the absolute potential at a point, this V of r will be equal to the total charge enclosed divided by 4 pi epsilon r. Okay. So, the potential is going as 1 by r. Now, here is an interesting thing. What will be the potential if you start sketching the potential, what will be the sketch of the potential? That is, electric field was discontinuous here, right. So, the electric field was discontinuous over here. What happens to the potential? First consider R much greater than A. So, in this case the potential is going as 1 by R. So, there is a 1 by R. So, this behavior is 1 by R. Okay. Now, as you start moving towards the shell, right. So, the potential keeps on increasing, and at R is equal to A, you are going to get a total potential of Q total, which is the total charge enclosed, which is rho s into 4 pi A square, if you want to write that down, divided by 4 pi epsilon A. This must be the potential on the spherical shell of the charge, right. So, this will be the value Q total by 4 pi epsilon A at R is equal to A. Now, what will be the potential to the left? Will it be 0 or will it be some finite value? It is interesting to see that one, that the potential will not actually go to 0. Okay. The potential will be constant and it would be continuous at this point, whereas the electric field was discontinuous. This potential is actually continuous. Now, why would potential be continuous and why is the potential not going to 0 inside the shell? Well, if you recall what is the definition of the potential, potential was the energy that was required to move a charge from one point to another point, right. So, if you start far away from infinity and then you move, say in the radial path, you keep moving, the potential keeps on increasing, right. The potential energy keeps on increasing, and as you reach the shell, you are at the maximum potential, right. So, you are at the maximum potential, you have done whatever the work that is required to move the test charge from infinity to the shell. Now, let us try to move, hypothetically of course, we will try to move the test charge inside the shell. Now, inside the shell, do you have to do any additional work in order to move the charge? Answer is no. Why? Because there is no electric field inside the shell. The shell has no electric field, therefore, you do not have to do any additional work in order to move the charge. Once you have brought it to the edge or at the surface, the surface of the shell, then inside you do not have to spend any more energy in order to move the charge, which means that the potential must remain constant. Also, the potential cannot change in discontinuous manner. Okay. So, the potential will be continuous and the potential will actually be equal to Q total by 4 pi epsilon A inside right up to the center of the shell. Okay. So, this is very critical. Please note that electric field can be 0 and electric field is 0 inside the shell, but the potential is not 0. Okay. All right. So, with this we will sort of close Gauss's law now. There is a lot of other symmetric charge distributions that you can keep working on. Okay. So, we are not going to consider them.